So welcome back. This is our next lecture on the equivariant degree theory. We are approaching it, and I hope you were successful in installing the GAP systems on your computers, as well as the EquiDeg package, as it was described in the previous video, which is not called the lecture, just simply GAP. So today's topic is, let's say like this, examples and couple of computations, usage of GAP for BurnsideRing. So we have here BurnsideRing. And before we do anything, we just do the following. We will be considering an example. So let me recall first. So for a compact Lie group, and I put here G like this, we defined the BurnsideRing as the free Z module, and I put here Z, generated by phi 0 of G, phi 0 G, with the multiplication on generators, free generators, let's say like this, H and K, given by the formula that if we take H and you want to multiply by K, then this is going to be a sum, and this will be L belonging again to the set of those free generators. Recall, this is the set phi 0 G is the set of all conjugacy classes of subgroups with the finite Weil group. So here we have an integer. That's the integer here. From here you see this is integer. That's a coefficient. So this is my NL. And then we have here the indicator, let's say, or standing by, this integer standing by the conjugacy class L. And here the number NL is equal the number of the orbit type. Maybe write it down, equals the number of L orbit types in the product of two orbits of the type H and K in, so what is the orbit? G divided by H times G divided by K. And we indicated that these numbers N and L can be computed more effectively. So we have also, we proved that this number NL can be given by the formula. So let me just write it down. This is NLH, and here I put here number of elements in the Weil group WH, and this is NLK, number of elements in the Weil group K, and then minus, and then we have here summation, and this is L tilde larger than L, strictly larger. And then we have the coefficient NL tilde. And then we have here the number NL L tilde and the number of elements in the while group of L tilde, everything divided by the number of elements L. So that's the effective form. It can be, let's use this formula and do an example, couple of examples. So remember what is the number NLH. NLH is the number, just simply you can say the number of the subgroups H prime, such that H prime is conjugate to H and L is a subgroup of H prime. That number can be, let's say, computed just by, let's say, inspection, just by inspection. Let me go to the example. So our first example, examples. Our first example is just simply take our group G to be dihedral group of n-gon. This is n-gon, but in our case we assume n is odd. And the assumption, this assumption that n is odd is crucial. It makes everything easy. Even, when n is even, it's more difficult. So we are just simply avoiding difficulties. And we will try to do it by hand, do the computations by hand, and that means we will try to avoid any problems, any possible problems. So maybe let's make a picture of what we are talking about. So n, for example, n, and this is odd, so I take 5. 5 seems to be odd, and that means we have here a polygon. So to make a picture of such a nice polygon and illustrate the elements in the group DNH, it is useful, it is convenient to make, let's say, this is the point, this is 1, 2, 3, 4, 5, this, and I will try to make a nice circle. So let's say make a nice circle. Not good. That's not nice circle. And then we have here it's at that point. It's pointing that point. So make arrow. Then we have this one and that one. No, maybe a little more. No, maybe a little less. Like that. And looks maybe okay. So, what did I get? I got a pentagon. Pentagon. This is my no, sorry. I want to have blue line. This is my pentagon. This is my pentagon. So that's my pentagon, and the D5, in our case we are talking at D5, is the symmetry group of this pentagon. Here we assume that the object here, circle, is the unit circle, so it is easy to identify the elements and represent them as rotations and reflections of the group Dn. Dn, in our case, this is D5. So let me write it down. This is 1. This will be my generator of the rotational group of the symmetries. This will be, of course, a square. This will be cube, etc., etc. This will be 4. There are 4 rotations. So what is the rotation? Rotation here is represented by a complex number. So gamma is equal to, I write it down, EI, and in this case 2 pi divided by 5. By 2 pi divided by 5. So when you multiply complex number by that number, it will rotate the vector by the angle 2 pi over 5. So let me just write now what is our group Dn in our case. So our Dn, as we guess, is equal, and we have here the following. So in our case, gamma is again a rotation related to n-gon. So I write it down a theta, and our theta is 2 pi over n. So that's n-gon, and that means our rotations are gamma, and this is gamma squared, and the last rotation, n rotations, are gamma, this is n minus 1. Then we have the reflections. The first reflection, kappa, is just simply the reflection, which is 0. This is matrix, orthogonal matrix. So you can see that kappa as an operator acting on the complex numbers gives you the conjugation. So that, of course, it relates to the, it easily relates to the notations that we are using the complex numbers. So here we have here gamma kappa, and then dot 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 gamma n minus 1 kappa, and here, of course, those are our rotations, and those are our reflections. So the reflections. So what are the rotations? Rotations are the roots of identity. Clearly, roots of identity. So it is useful, it is convenient to write that this actually can be written like, I take just simply Zn, roots, rotations are roots of identity. So this will be n, and then I put here union, and this will be Zn, and I put here kappa. So those are reflections, and those are reverse. So those are the rotations, and those are reflections. And that's good. So this is very good. So of course here we can think about the all possible. Notice that since this is a finite group, so in our case the phi n is actually equal to phi 0 of dn. That means all the subgroups of dn are just exactly the subgroups required in the definition of the Burnside ring. So this is exactly the generators, the set of generators. So what are these generators? You can verify it just by analyzing the group Dn. Very easy to verify. What are the subgroups of Dn? So subgroups of Dn, of course, we know what are the subgroups of Zn, so that helps a lot. So that means that will be another decay, yeah, because if you have an n-gon, you can have a symmetries of k-gon, which is in certain way like inscribed in the n-gon. And then you have here, the subgroups zk, and then in this case k is a divisor of n, must be divisor, this is divisor of n, and of course k can start with 1, so that means belongs to n. So those are the conjugacy classes. And it's kind of interesting, this is kind of interesting to notice. For example, if you look at the, because n is odd, remember n is odd. So of course if you look, for example, at the group, in our case, in our example, you have here D1 contained in D5, like in our example. So D1 in our case, it will be just simply 1 and kappa. So you would say how many elements are in this conjugacy class of that group. It's very easy. You just take this conjugacy class and just compute it. So you will find out that this is actually equal. This class is equal to the following group. So you can have here, maybe write it down. First group is 1 kappa. The second group is 1 gamma kappa. And then you can see that 1, this is square kappa. And then you have here 1 gamma 3 kappa. And finally 1 gamma 4 kappa. And there exactly 4 subgroups sitting inside this conjugacy class. So as you see, this will not be the case if you have n or n even. So that means if this is n even, then there may be differences. We will talk about it in a moment. We will talk about it in the moment. I will explain it to you. So if we know this clearly, what are the generators here? So in such a case, we return to the general case. So we know that our multiplication table for the generators will look something like that. So we have an integer k must be divisor of n. Remember, n is odd, otherwise I will be not saying the truth. So in such a case, we have here kind of a, maybe let's say like this, m is also divisor of n, and then we have here, multiplication. So here we have here subgroup dm. Here we have here the subgroup zm, and then we have here the subgroup dk, and then we have here a subgroup zk, and we want to know what is this multiplication. So we want to know what will be here, the product of these two, the product here, the product here, and the product here. So of course, we remember this will be something that is related to the, so let's write it down. So for example, let's start somewhere. Let's start somewhere. For example, we want to, let's say we compute dk, let's multiply it by dm. So we want to know what it is equal to. So first of all, we know that this is going to be, so let's write it down, this is dn divided by dk, so that's my group G divided by H, times, this will be dn divided by dm, and then of course take here an element here, x. So what is an element x? So an element x, in our case, it will be coset, so put it here like that. So that will be G dk, a certain coset of the dk in dn, and then this will be maybe this is h, so let's write it down like that. I prefer to use this notation, h dk, and then this one is here k dk, and my, so this is the product, and my goal is find what is the isotropy of it. The isotropy of that element will indicate me what is the orbit type of that element. So let's do it. Let's do it in general. So here we have this product, so this is k. So what I said is basically take this x belonging to this particular product and then compute its isotropy. So x is equal hx, and this is equal kk, and let's compute this. So what do I get here? I'm getting here that this is g of x is equal to the set of all g belonging to g such that g applied on hx, comma, kk must be the same pair of cosets. So this is hh, and that one is kk. And what does it mean? It simply means that this is the set of g belonging to g such that GHH is equal to HH and GKK is equal to KK, and that one clearly indicates that G and G is such that H minus 1 G H is equal to H, and I put here under, so this is k minus 1 g, k h is equal, sorry, k is equal to k, and of course that provides you with the following, the g belonging to g, such that k minus 1 gk belongs to h and k minus 1 gk belongs to capital K, and that one is of course the same as g belongs to g, such that g belongs to the k h k minus, sorry, h, and so this is h. I'm so sorry. So this one is h, this one is h, and g belongs to k minus 1, and after that we are getting that isotropy of that one is actually equal to the intersection of these two conjugate subgroups. So in such a case, the orbit types in the product of gh times gk are possible only to be this product. So this will be orbit. So I can just simply take h equal identity, so this will be like a k minus 1, sorry, not k minus 1, k minus 1. So those are all possible. So this means in this case the conjugacy class of this group simply. So in our case, it is easy to notice. So it is easy to notice if you have, for example, if we have here h is equal to dk, and if k is equal to dm, so what are the orbit types in dn divided by dk times dn divided by dm? So clearly, in this case, the orbit types, there are two possibilities. If you take dk and intersect with dm g minus 1, so there are possible. So in this case, there are two possibilities. Either you get dl or you get zl. Very easy to verify. So ZL, two possibilities. Very easy to verify. Okay, so ZL, where L is a divisor. This is a divisor. What kind of divisor? It's a greatest common divisor of K and M. One can easily verify. In order to see it clearly, if you take ZK intersection Zm, you are getting immediately that this must be equal to ZL, and then since dk can be written as zk intersection, and here we have here zk, and that one is kappa, and take the rotations, for example, g is a rotation, so dm, and this is g minus 1, of course it will be in this case zm union, and this will be zm, so this will be zm kappa g minus 1, so g is a rotation, so this will be like a gamma in our thing to the certain power j, so rotation. So that's a rotation. And in such a case, we are getting here that this particular will be equal g squared zm kappa, and clearly if you rotate zm, the locations of the, you see, if you rotate the locations of the roots, here you are getting empty intersection with zn. So that will be definitely what I said. So we have here the possibility that either you will be getting the same location of zm, or you will be getting the location which is not intersecting zn. So that means in this case we obtain that indeed we have here this particular orbit types. So that means we can write it down, for example, that the dk, we write it dk times dm is actually equal, and we have here x, this means in this case will be dl plus unknown y integer, and this will be zl. There are two orbit types. And in order to compute it, we can go back and use this particular formula, so namely the recurrence formula. Our recurrence formula is here. This is our recurrence formula. And this recurrence formula can be applied. So we already see that the lattice of orbit types in that one, in dn divided by dm times dn divided by dk, is just simply dl and dzl. So there are two orbit types here. So this is L is equal greatest common divisor of m and k. And now we can apply the recurrence formula. So we start and compute it. Before we do the computations, let me point out that actually for any L dividing k, I have the following numbers. So that means n d L, and this is dk for the subgroups, will be always equal 1. You can check it just by simply looking again at the polygons and what is actually happening when you rotate the polygon. Is it the same? You are getting the same symmetries as the initial, or the symmetries are changed. So that means any conjugate subgroup of decay actually gives you a different polygon which is rotated from its position, original position. So this will be corresponding to the conjugate subgroup to decay. Symmetries of the polygon will be conjugate subgroup to the decay. So now we have also zk, and you can see this NLH number. So those are these NLH numbers, NLH number and NLH numbers is also 1. So this is 1. And finally, if you look here in ZL, and I put here dk, so that number is actually equal n divided by k. N divided by k. Interesting. You can check it out as well, and that's not hard to verify. And yes, you can verify it. So basically, you can notice that, basically, let me write it down. So remember, we have gamma is equal to E I theta. Theta is equal to 2 pi divided by n. And then we have here that ZL, which is which is divisor of K, is actually contained. So this is a subgroup of dk. Then you have here also that ZL will be, N is odd. Remember, N odd. So K is odd. And this one will be smaller, equal to gamma dk, gamma minus 1. So that's your copy number 1. So this is your H, this is your number 1 H, and that contains ZL. And then you go and the last one that will be, and after that you will have repetition, so there will be no more the same. So this will be an m minus 1 dk, and this is gamma minus m minus 1, where m is exactly n divided by, no, that's, maybe I should not use L. So maybe I use different symbol, because m was used something, s minus 1, and this will be dk, and this is gamma s minus 1 minus, and this will be your h s, and this is 0, so you see this is like a number 0, which is equal to h, where s is equal n divided by k. Verified, can be verified by hand, no problem. So in such a case, we got all these numbers, and now, of course, what are the Weil groups? So if you see, let's start again. What is the Weil group of dk? So here k, so n is odd, so k is odd, everything is odd, so Weil group is exactly z1. So that means in this case the normalizer of dk is equal to dk, so Weil group is, and we are getting the number of elements in this Weil group is equal to 1. On the other hand, if you take the Weil group of dk, of zn or zk, then you can see that actually this is a normal subgroup. Maybe like this, write it down. The normalizer of zk is actually equal to dn. So in such a case, the Weil group is exactly of zk is exactly, so that's the number of elements. The normal, so this is normal, so this one is equal dn divided by zk, and this gives me how many elements are here. So this is 2n divided by k. Okay, I got the Weil group. So now let's compute the products. So let's do the computation. So compute the, let us compute the multiplication table. For the Burnside ring A, dn for an odd integer. So this is for n odd integer. So in our case, we choose k divisor of n, and we choose L divisor of n. We already showed that the orbit types here will be dk times dn equals unknown coefficient integer. So this is dl and plus y and unknown coefficient zl. And in this case, L is the greatest common divisor, of m and k. So let's do it. So now, since we have here the lattice of isotropy here, not here, we changed the page, so this must be here. You see this lattice, this is the maximal element. So we start with the isotropy at the top of this lattice, so means dl. So what is x? So let's go and do the computation. So in our case, x is equal, and I have it. So this will be equal. Of course, this will be n, and here I have dl, because this is corresponding to this particular. So dl maybe bigger numbers. I should not be shy. So this is equal. So this is n dl dk while group of dk times n dl dm, and this is while group of dn, and there are nothing bigger, so there is no L tilde, divided by while group of dl. So now what did we choose? What did we show just a few minutes ago? Oh, yeah, we know the numbers. So these numbers, 1, 1, all of them are 1 in this case. Wow, so nice. This is 1, 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 this is 1. So I got this is equal to 1. Oh, yes, I computed it. X is equal to 1. So now that value is equal to 1. So let's compute y. So in this case, y, we have here y is equal, and we start again, n. And our conjugacy class is ZL. So this is n, and this one is ZL dk times w dk, and then we have here n, and this is ZL dm, and this one is w dm, and then we have minus, and here we have 1 orbital still. So what do I get here? I have here n, and this is L tilde. So our L tilde is equal dl. So our L tilde is dl, so this will be L tilde, and we just computed it here. And then you have here n L tilde, and then we have here absolute, let's say dl tilde while group, and everything is divided by number of elements in Z, sorry, in our case, yes, ZL. So here is d tilde, so let me write it. Maybe I should make it more precise. So, okay. So L tilde is equal dl, so I'm getting here, this is n. So that my x, actually, write it down, x, and then you have n, and this is ZL dl, and this is while group of dl, and here divided by while group of ZL. So okay, we can put it. So we have it. So that NH number. So what is here the number? This is n divided by k. This one is n. Sorry, n divided by n. Let me check it. Is it? N. So this is here. Yes, that one. So, and then the while group is equal to, so this is not, this one is 1, this one is 1, and that one is m, n divided by L, and that one is again 1, and this value here is 2, n divided by L. Okay, we got a number. So if we put it clear, if you put it nicely, so first of all, you can do some cancellation. Namely, you can cancel this k, one of them, so minus this and minus that, you can get cancellation. So you are getting here that the product here is simply n divided by kn minus 1 over L divided by 2 divided by L. So that gives me, so what do I get here? This is Km, and then I need to put it, one second, let me check if I'm getting the 1. Okay. n divided by k, and this one. Yes, yes, that's correct. So let me continue. So I can rewrite it down like that. N divided by L minus Km, and this will be KML divided by 2 divided by L. Okay, okay. So I'm getting here NL minus KM, and here we are getting here, this is 2MK. Oh, I got the formula, NL. So, yep, I got the formula. So similarly, if you check what's happening here, dk, if I take dk and I multiply by Zn, then I will obtain that this is actually equal to Zl again, and the number x here will be Nl divided by Km divided by Zl, and in such a case we obtain the table, and we can fill this table, and the table provides us, okay, maybe we have already the table. So let's go to the table. Where is my table? Maybe that's right. Let's make the table. So here we have K divides N, M divides N, odd, and then we have here the table. So this will be like a dm, this will be like a zm, and this one will be dk, and this will be zk. So here the L, put here clearly, L is equal greatest common divisor between M and K, and this one is dl plus nl minus mk divided by 2mk zl. Here we have nl divided by km zl, and then here I have here nl divided by km zl, and finally nl divided by km zl. That one is very easy to compute. That's my multiplication table. This is my multiplication table. So what happens in the case when n is not odd? Similarly, it is possible to do the computation, except in that type, if n is not odd, suppose n is even. In such a case, we have two types of the conjugacy classes. Namely, we can say like this: if k is divisor of n, and then you have here s, which is equal n divided by k. There are two cases. S is odd. Then in this case, we have here the group dk. This is the conjugacy class of the group, let's say dk. If s is even, then we also have there is another group, subgroup, which is, we call it by dk tilde, which is not conjugate to dk, and let me put it out how it is. So how it goes, so if you have, for example, this is dk, so what do? I say, okay, I have here s is equal to that one, so this will take a gamma to the power s. Remember, gamma is equal to ei theta. Theta is equal to 2 pi divided by n. So that's a s is also divisor, so this is gamma to s. And last one is gamma k minus 1 s. and then you have here kappa, and this is gamma, S kappa, and the last one is gamma k minus 1 S kappa. So this is group dk. So what is the group dk tilde? In this case, this group has the same rotations, and this is gamma k minus 1 S, except here you have gamma kappa. Those are the rotations that are, these rotations cannot, they are not conjugate to those one. So here we have here gamma, gamma S kappa, and this one, the last one will be gamma times gamma k minus 1 S kappa. So we have here those rotations like it. and these two subgroups. So in such a case, we can write it down phi 0, so phi 0 of dn is equal, then you have here like this, the groups, subgroup zk. So here k is a divisor of n, and then you have here, so maybe put here union, and I put here like this dk. So those are conjugacy classes, and this is conjugacy class, and this is k divides n, and s is equal n divided by k odd, and then union, and the last one will be dk, and dk tilde if k divides n and s equals n over k even. So those are the subgroups. So now we can do the, let's say, let's put it like this, we can do the, let's say, computations exactly in the same way as we did it before. And as you notice, this is kind of annoying. This is kind of annoying, kind of difficult. So what is my point? Actually, we installed GAP. We installed our package, so why not to use GAP? Before we go to GAP, okay, so let me show you the multiplication table for D3 and D5. This is exactly what we have just computed, and as you see here, it shows that the complete list of the conjugacy subgroups is here. So this is D3, D1, Z3, Z1. So that's a very short one. The same for D5, and that's the those numbers are prime, so there is not much problem here. And of course, but if you would like to do the same thing, we need to do the same thing. We'll use the computers one moment in order to achieve it. So, for example, for D6, you can see that in D6 we have more subgroups, and here that's the lattice of the conjugacy classes in D6. And let me show you more bigger. Let's use this bigger picture. So you can see here we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 conjugacy classes. And of course, notice that there is D3 and D3 tilde, there is D1, D1 tilde, as I mentioned, and then of course there is D2. Those are the subgroups that will play a role. Let's say, we means in this computation, in order to do it, you have to do it for each of them separately. So if you can see, the NLH numbers can be also computed. That's how the numbers are computed. Those are the results showing this numbers NLH. I may say that you don't really need to, let's say, memorize or note, or let's say take notes of these numbers, because basically these numbers are available anytime you want by using the, let me see if I can actually move it. Can I move it a little down? Okay, need to make it smaller, otherwise I cannot show it. Okay. D6. We have D6. So that's the multiplication table for D6. Okay. Okay, it looks okay to me. Huh? Okay. So general multiplication table for AD6. In fact, we have the for any. So here you have here for any dn. So this is ADN. The formula that we derive can be also written in this particular form. So as you see, those are the possible multiplications of the generators. Okay. So now, of course, I mentioned to you that we can use the program in order to do the computations on the Burnside ring. So let's go to the program. So let's do it like that. So we start with the so those are actually the commands we'll be using. Control C. So let's go. So what do? You already have the gap, so let's start the gap. I start in the gap. Oh, works, very good. I'm always happy when it starts. So now, load package. That's the command, and this is EquiDeg package. This is the package we installed in the last presentation. It is true. And then we have here a couple of special commands. So look here. First of all, you defined your group, and you notice that we want to define the dihedral group as a permutation group. So that's why we put here P. Notice that this command will not work in regular gap without loading this package. It belongs to this package. So this is dihedral group expressed as a permutation group. So we have the dihedral group of 5 elements of pentagon. It is. So let me copy it. It is easiest way, and let's place it in the program, and we have it. So have it here. So let me do it. So Control V. No, sorry. Nothing. So okay. So put it like this. G is equal P. Let me check. Okay. Dihedral. We have the dihedral now. So now the next thing is we need the generators of the Burnside ring. So this is CCS. So conjugacy classes of the subgroups. So this will be conjugacy classes subgroups of our G. So we have the notations. Oh, we got it. Very good. And next thing, let's see what else we have here. And here we have the conjugacy class. What about creating the Burnside ring? So let's create the Burnside ring. So let's do it. So the Burnside ring is here. So AG, without the brackets, this is just a name, AG. So it will be equal Burnside ring OG. Very good. So I'm putting Burnside ring. Oh, it's done. So next thing what we do is we have these conjugacy classes, but these conjugacy classes correspond exactly to the generators. So the generators, which we let's say we will be denoting them as H1, H2. So it means in a certain way those are the conjugacy classes of respective subgroups. So let me do it, and then I put it here. So let me copy. Let me copy it. So this is our generator. So this is put it like this. H is equal basis, and this will be AG, or this Burnside ring. So you can see bases. So how many, well, let's see like this, conjugacy classes. So how many of the conjugacy classes? So conjugacy classes 1 and take 1. What is this? This is exactly, this is exactly the trivial group. Then if you take the second one, then you can see that this is given by the, that this is given by the permutation, which is a 2, 5, 3, 4. Can you guess what is this particular permutation? So if you look back at our picture of the pentagon, let me go to the pentagon. Where is my pentagon? Oh, here. So this is my 1, this will be my 2, the vertex 2, this is my 3, this is my 4, this is my 5. So what this permutation does, so what kind of the symmetry of the pentagon is the permutation 2, 5, 3, 4. So let's look again. 2, 5 means switching this 2, switching this 2, switching this 2 is that one. So what do I get? I'm getting here that this is exactly kappa, kappa, kappa. And that means the generator of this group here is kappa. And that means, what does it mean? This means simply that this conjugacy classes, so let me write it down. So you have here like this, H1 is just a trivial. So this is trivial group. So this is just put here 1. And then you have here H2 is just D1 because you have two elements, 1 and kappa. So that's exactly the group D1. And then let's go and check the next one. And that's interesting. And the next one would be, I need to put here column in order to make it easier, and this would be 3, the third one. So what is this? Oh, this is 1, 2, 3, 4. What could be a permutation which is a cycle? 1, 2, 3, 4. And of course you look again, this is 1 goes to 2, 2 goes to 3, 3 goes to 4. So that's a generator gamma. So this is nothing else than the group generated by gamma, and that means this is what this is, a Z5. Z5. So let me write it down. So D3, so this is H3. H3 is equal Z5. So this is D1, D5, Z5. And now what is, I should write it differently. I should write it down like this. H1 is the Z1 trivial group, H2 is D1, H3 is Z5, and H4, what is H4? So what is H4? Let me check it out, and this means this one, I put here number 4, 4, so the 4, what do I get? And we have gamma and we have kappa. So what is the group generated by gamma and kappa? So it's the group generated by all rotations and the group generated by all reflections. So this is D5. So this is D5. So that means the last one is D5. So you can see that's it. There are four conjugacy classes here. And now what do? Let me play. So let's say H1. So which one is interesting? Let's multiply something. H2 maybe. What is the D2 is H2 times H2. What do I get here? So I put here H2. What do I get here? I'm getting here capital. I'm getting here that this is 2H1 plus 1H2. So I just got the multiplication that D1 times D1 is equal, and this is 2Z1 plus D1. Am I right? Am I right? Yeah. 2 first and the second. Yes. That's exactly what we have seen in our table. Where's my table? Yeah, this one. This one. So of course, those are the examples of the very, very elementary groups. So there's absolutely not a big deal here. We could do some more. Let's say let's do D6, maybe D6. So let's say like that. Let's exit. Maybe quit. And start gap again and load everything correctly. Okay, and then we put here, yes, we did incorrect. Maybe. Very good. I loaded it correctly. As you notice, I'm not very skillful. And then do the same. G is equal pDihedralGroup. And now we take 6. And we have 6 elements and do the same. CCS is equal to ConjugacyClassesSubgroups. And this is G. Works. Then we have here AG is equal BurnsideRing of G. And then we put here H is the basis, and this will be AG, and that's it. Basis is AG. Very good. So now we can look at the maybe of some of the generators. So for example, let's see CCS. And let's see how many of them are. Size. So let's do size of CCS. How many of those classes are? There are 10. And now let's go to our table. You can see here in our table, maybe if I'm able to move it nicely, maybe like this. No, it is, okay, I got lost. Oh yes, maybe in the lattice, don't move, don't touch it. In this lattice we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, exactly. So it's interesting, can we recognize this, the subgroups among these conjugacy classes? So for example, I guess that the first one is the smallest one, the smallest class. And the last one is probably the whole group, as you see it. You see this is the whole group. So what about the conjugacy classes here? So you see the generators. The generators can be shown by using this command. So I say like this, let's say number 3. What is the class number 3? I'm using 2 indices. First of all, I take the third conjugacy class and take the first representative. So in this case, it will show me the generators of the group. And as you see here, we have 1, 4, 1, 2, 5, 3, 6. Interesting what it could be. So let me go to the picture. Let's make a picture and let's think about what this particular, so let's make a hexagon. So this is my hexagon, and hexagon like that has the vertices 1, 2, 3, 4, 5, 6, and as you notice here, this is 1, 4, 2, 5, 3, 6. What kind of the transformation it is? Is this a rotation or reflection? Is this a rotation? So this goes from here to here, here to here, here to here. So what kind of a reflection it is? Is this a reflection? Yes, definitely. Is this a reflection which is conjugate to the kappa or not? And in this case, you can immediately notice that that's not conjugate. This 1, 2, 3, 6, 4, 5 is not conjugate to kappa, which is the reflection. This one, this reflection. So definitely this reflection generates the subgroup. So let's write it down. 1, 2, and 3, 6, and 4, 5 generates the group D1 tilde. So this is D1 tilde. D1 tilde. Very good. So let's go and maybe guess another one. So for example, let's see. What about number 7? 7. I put here 7. So I put here 7. So I change this 7 to 7, and I see, what do I see? I have here 1, 3, 5, 2, 4, 6, and then you have 2, 6, 3, 5. Could you please guess what kind of the subgroup it is? So in this case, let me go back. So let me write permutations 1, 3, 5. Okay, so we have a permutation like a 1, 3, 5, and this is 2, 4, 6, and you can think about what is this permutation, how this permutation is related to symmetries of the hexagon. So this is 1, 2, 3, 4, 5, 6. So of course here we have this angle theta. So the gamma, the generator, is e to the I theta, and then of course theta. So this gamma means this is the rotation by that angle, which is 60 degrees. But what is this rotation? This rotation, what this rotation means? How this rotation acts on the hexagon? Can you see, oh, it is a rotation by 2 theta, by 2 theta. So that means it is the rotation by gamma square. This is gamma square, and this means what group is generated by gamma square? So we know that gamma 6 is equal to 1. So if this is the generator of that group, so that means psi to the power here 3 is equal to 1. So definitely this psi generates Z3. If you look at the list of the groups, so let me look again at the list of the groups. So there is a Z3 and there is also D3. There is a Z3 and D3. So is this Z3? Z3 has, how many elements Z3 has? Z3 has 3 elements. We already know 2 of them. So the other element in the Z3 is that, is which one? So let me show you what is the other element. So other element in Z3, let me write it down, will be exactly Z xi to the power, so this will be xi to the power 2, and xi to the power 2 means this one, so this means so 1 goes to 4, 1 second, no, 1 goes to 5, sorry. So, or maybe, yes, 1 goes to 5, 4 goes to 6, and okay, this means 1 goes to minus 2. This one and that one. 3 to 1. So 1, 3. Sorry, I'm getting. 1, 5, 4. Oh, other way. Sorry. So this is. So this is 1, 5, 3, and this will be 2, 2, 6, 4. Am I right? So this will be 1, 5, 3. So no, just that's my fault. This is my fault. So gamma. So this is psi square is equal to exactly 1 goes to 5, 5 goes to 3, and 2 goes to 6, and 4. Ah, that's inverse of that one. Yeah. Okay, that's clear. So yes, that's the Z3. So, but that's not the same. What it could be? This is 2, 6, and this is 3, 5. Let me look again. What does it mean? So 2, 6 and 3, 5. That's exactly kappa. So in such a case, we have here that this group contains Z3, and then it's also kappa. So it contains Z3 and kappa, which gives you D3. So yes, I know this element. So which one it is? It is again. So the element number 7, so H7, the element number 7, put it like this, 7 is exactly D3. So we got it. So what about if I take if I multiply, say, D3 times, what do I have here? I have here D1 tilde. I want to multiply these two things, D1 tilde and D3. Let's do it. So D1 tilde is exactly the number, I believe it was number, where is number? Did I write the number? Okay, let me see. This was equal, number 3. So let's write it down. H3 times H7, what do I get? I get a trivial group. 1. I get the trivial group. Is this true? So let me check my table. I have this table, and I'm worried that my table maybe is not correct. So let's see if it's correct. So what did I compute? I took the group, which was D3, and I multiplied by D1 tilde. Here, this element. D3 multiplied by D1 tilde. Let me show you exactly what it is. So this will be like a yellow. So I say this and multiply by that one. Yes, I got a Z1. So that's 1. Very good. So yes, indeed, we can compute the Burnside ring using this computer. Let me explain how the notation in the program, the GAP program, can be simplified in such a way that it will be easier to recognize which conjugacy class is represented by this or that particular element in the matrix. We call this matrix CCS matrix. So that means simply we're just creating the matrix of conjugacy classes of subgroups, and now we would like to give them names. For example, let's look at the group, dihedral group of 6 elements, and let me explain how the names can be introduced to the program. So we start again our let's say the program will be here. So let me do it like we did it. Start the gap, then we will enter the library, add the library. So I just simply copy it from here. I load the library and then paste it into the gap program. And we got it. And now let's define the group and the conjugacy classes. So I just copied these 2 lines. The group is the dihedral group of 6 elements, and then we have here conjugacy classes of subgroups of G. So the group D6 and its conjugacy classes. And now let's put it here and copy, and let's see what happens. So we have the group, we have conjugacy classes, and now of course if I write CCS, so you can see that here of course we are getting sorry, where it is gone? It disappeared, sorry. Okay, so we have is the conjugacy. So the first conjugacy classes here is indicated like that. That's the trivial group. The second one, we have done this before. We could easily recognize this element here, 2, 6, 3, 5, represents nothing else than the conjugation, complex conjugation. Let's look at the let's say the hexagon. So you see 2, 6, 2 goes to 6, and 3 goes to 5. So that's complex. This complex conjugation, definitely this is a generator of the group D1. So let me introduce the names. I just recognize these names now, and let's say this is the matrix of the names, and we call it just simply conjugacy classes of subgroups names. So this is and we put it here, and let's discuss shortly why it is actually true. So you see here, the first is Z1, that's a trivial group. The second one is D1. This is 2, 6, 3, 5. That's a kappa, so this gives you D1. And Z2 is generated by that particular element. If you want to see, let's go and look at this. So you see 1 goes to 4. So you see it like that. 1 goes to 4. 2 goes to 5. So that one is going to. So it is a minus identity. Minus identity, actually, it is indeed the generator of the Z2 group, cyclic group of Z2. And then next one, you can see there is another one. This one is, we talked about it before, so oh yeah, this is 4, 5, 3, 6. That is the D1 tilde. So this is D1 tilde. Yes, it is D1 tilde. Then you have here, for example, Z6 is the rotation of 6 elements. So it is the element here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is that one. And then you have here D3. Okay, so mainly, let's say, those are all the names. So let me enter it, and we got it. Now, of course, I will associate these names now to the conjugacy classes. So I will use this particular command, and this is command here. So Control C. So this goes like that. So you just simply need to learn the command. And once we have it, now we can repeat our command CCS. Let's see what happens. And instead of the of the list of the subgroups. I'm getting short names for each of those conjugacy classes. Each so we know it. So for example, you want to know what is CCS7, it just gives you, this is D3. So this is D3, and in such a way, it is now kind of easy to manipulate on the subgroups, and we are able to recognize their names. Sometimes when the subgroup is pretty large, it may be kind of difficult to name all these subgroups in this big group, especially when the structure of this group is not intuitively, let's say, clear. For like in the case of the symmetric groups, you have hundreds of subgroups. So in such a case, maybe it is appropriate just keep the original notation, means notation expressed as the permutation subgroups, and this notation which is here may be used for that purpose. And later on, when you find some of these particular conjugacy classes of your interest, and when you find out that they are important for you, you can try to figure it out, the properties of the subgroups and and the structure of the subgroup, to find out more about the symmetries. So that's enough for this lecture, and next time we will introduce the, let's say, more examples. I will talk about the group O2, and also we will talk about the product groups. I will introduce the notation, how the products can be, let's say, what kind of the notation we can use in the products, and sometimes it is useful to keep the notation, this notation which we'll call the amalgamated notation for the computations, as it is easy, providing us easy information about the structure of the particular conjugacy classes that we are considering. So thank you, and I hope that I will continue soon in the next lecture. So see you later.